Here's an example of finding the volume of a solid of revolution using integrals. This is from section 6.2 using what's known as the disk or washer method. In this problem, we'll use the disk method. Find the volume of the solid generated by rotating the region bounded by y equals x cubed, x equals 2, and the first quadrant about the x-axis. We'll need to graph the region bounded by the curves y equals x cubed and x equals 2, and in the first quadrant. The first quadrant is the section of the plane where the x and y values are both positive. That's this quadrant here. So whatever region we're looking at, we'll only use the portion that's in that quadrant. So y equals x cubed is a very straightforward polynomial. This is one whose graph you want to already know. This should be in your toolkit already. It goes through the origin. Let's put 1 here and 2 here for reference. I'm not going to try to draw it to scale, but I want a rough idea of what it looks like. I know that the tangent line to this curve at the origin is horizontal, and that it will curve upward, kind of like a parabola, except that it goes considerably steeper. And in the third quadrant, it will do the same thing, but rotated 180 degrees. Of course, we don't need the portion in the third quadrant, but it's helpful to draw it. This is y equals x cubed. We also want to draw the line x equals 2. That's a vertical line right here. Here is x equals 2, just like this. So the region we want is the region that's bounded by these curves and in the first quadrant. That's just this portion here, a bit like a triangle with a sunken hypotenuse. Now that we've drawn the region, we should figure out what the solid of revolution looks like. The problem told us that this region should be rotated about the x-axis. It's always a good idea to draw a little circular arrow going about the axis of rotation that you're interested in. That's this axis right here, the x-axis. Many problems that we solve, we'll find ourselves rotating our curve about the x or y axis, but sometimes we'll use a different line, and we want to know what the axis of rotation is in every case. So to draw what this solid of revolution looks like, we could start by visualizing what happens if we reflect this region across the axis in the plane. It looks something like this. It doesn't need to be perfect, but you will have an easier time visualizing this if you can get your reflected graph looking as accurate as you can. Now imagine this region is actually being rotated round and round and round that axis so that it's sticking out of the plane in front of you. It has circular cross sections, but viewed from an angle, you'll have something that looks a bit like this big end here. There's one circular cross section. Here's another one. Here's another one. Here's another one. You'll have something that looks a bit like the bell of a trumpet if it came to a point at the end. I think it's a good idea, it's very helpful here, to try and describe the object that you get in familiar terms. If you do this, find some words to describe the object that will help you to picture it in 3 dimensions. So for example, I call this the bell of a trumpet. It's got flared out edges. It comes out to a flare, but instead of extending onto the rest of the tubes that make up a trumpet, it comes to a point on the left side. That's our solid. Now our next step should be to try and imagine what happens if we slice this solid up in slices that are perpendicular to the axis of rotation, and we'll get a whole bunch of different little disks, little pancakes that all line up along the x-axis. How can we work out what those pancakes look like? Our next step is to try to understand what one of those slices looks like. We could start by thinking about the two-dimensional region of the plane that we used to get our solid of revolution. If you wanted to set up an integral to find the area of this region, you might do so by thinking about it as a Riemann sum, and you would slice it up into vertical rectangles. Here is a typical one of those vertical rectangles. This is the rectangle that's at position x along the x-axis. Its height is given by the curve that describes it. The top curve minus the bottom. The top curve is x cubed, y equals x cubed. The bottom is just the x-axis, y equals 0. The height is the y coordinate then, which is equal to x cubed. And of course, the width of that rectangle is dx, as we've discussed before. What happens when you rotate that rectangle about the x-axis, as you've rotated the entire region about? Well, you're going to rotate that rectangle around the axis that it's perpendicular to, and it's going to trace out what will look like a big circle. In fact, a circle with some thickness, i.e. a disk. Here is a typical disk. A disk at position x. It has a circular cross-section, but it has a certain amount of thickness as well. In fact, what is the radius of this disk? Let's call it big R. The radius of the disk is just the height of the rectangle that we had. The rectangle extends from the center of that disk all the way to its edge, so the height of that rectangle is the radius. Which we determined is the y value, which is x cubed. What is the thickness? Well, the thickness of that disk is just the width of the rectangle, which is dx. So what is the volume of this one disk? The disk is basically a cylinder. So the volume is pi r squared, the area of that disk, times the thickness, which is dx. So it's pi r squared dx. If this were an ordinary cylinder, we might call that thickness h for height, and we put an h there. In this case, our thickness is pi times x cubed squared dx. Now that we understand what one of our typical disks looks like, we actually understand what all of them look like. By varying the value of x, we can find all of the different disks that make up the slices of this solid of revolution. All we need to do now is add up the volumes of all of these small disks to get the volume of our solid. And of course, taking the sum of all these would be like a Riemann sum. And really, what we're really doing is we're taking the integral. So the volume of our solid is just the integral of the volumes of our individual disks by r squared dx. We'll need to know what the bounds are. If we go back and look at our graph, here's our graph. We notice the x range is between 0 and 2. So the bounds on x are from 0 to 2. So our bounds go from 0 to 2. All we should do now is just fill in the actual function for r. This is our general formula for the volume of any solid of revolution using the disk method. But for our specific solid, we should fill in the r. We also like to pull out that pi because it's a coefficient being multiplied by the rest of the integrand And we like to pull out these coefficients because we don't need to worry about them until after we've done the integral. Pi times the integral from 0 to 2 of big R squared, that is x cubed squared, times dx. Our final step is to solve this integral. So here we go. This is a pretty straightforward one. The integrand is a very simple power function of x. So this equals pi times the integral from 0 to 2 of x cubed squared is x to the 6th times dx. Notice, by the way, all I did here was use some simple algebra, some laws of exponents, to simplify my integrand. I have not actually computed the integral yet, so I still had to write the integral symbol. Okay. Now, in the next step, we are actually going to compute the integral, so I will not write the integral symbol now. This equals pi times x to the 7th over 7. That's the antiderivative of x to the 6th. Evaluated at 0 and 2. We'll bring that right over here. All we need to do now is fill in our bounds. We have pi times 2 to the 7th over 7 minus pi times 0 to the 7th over 7. 2 to the 7th is 128, so we have 128 pi over 7 minus 0. So our solution is right here, 128 pi over 7. You could plug that into a calculator if you wanted to and get a decimal approximation, but this exact answer is really a preferable answer, so we'll just keep it just like this. And this is our solution. This is the volume of our solid of revolution.